Welcome. My name is Samarpita Roy, and in this lecture, I will continue to take you through the concepts of stoichiometry and kinetics, which form an important part of the environmental biotechnology course. Up to now, we've seen how stoichiometry helps define a quantitative link between the reactants and products and how it connects to operational costs. Next, let's explore kinetics, which helps us understand how reaction rates influence the design and performance of bioprocesses. In bioprocess design, the first kinetic Monod-like relationship we consider is to identify the consumption rate of the growth-limiting substrate Qs and the growth-limiting substrate concentration in bulk liquid, noted as Cs. The growth-limiting substrate, S in this equation, is by definition lower than that of any other substrate in the media and is the one that defines the overall growth. This relationship defines that the uptake rate depends on two main terms: the biomass-specific maximum uptake rate of growth-limiting substrate, or Qs max, and the second term related to the substrate concentration and the affinity constant Ks. So to define, Qs max is the maximum rate at which microorganisms can consume the growth-limiting compound and can be defined as moles of substrate S consumed per mole biomass formed per hour. Cs is the concentration of that compound in bulk liquid, and Ks represents the affinity constant, indicating the concentration at which uptake occurs at half the maximum rate, defined as the moles of substrate S consumed per liter. Now, if we plot Cs, the substrate concentration of the growth-limiting compound, against Qs, the biomass-specific maximum uptake rate of growth-limiting substrate, we will see that Qs increases rapidly as Cs increases. When Cs becomes infinite, the switch function involving Cs and Ks becomes 1, and therefore the biomass-specific concentration rate tends to Qs max. The half saturation constant, Ks, defined as the substrate concentration at which the uptake rate is half of that maximum value, can also represent the affinity of a microorganism towards the substrate. In such a case, the low half saturation value would indicate a very high affinity towards the substrate. At low growth-limiting substrate concentrations, the affinity constant plays a very important role in determining the substrate consumption rate. To apply what we have learned so far, let's take nitrifiers as an example. Imagine we're treating wastewater with around 100 milligrams per liter of ammonia nitrogen, which serves as the growth-limiting substrate. Given the affinity constant and maximum biomass-specific consumption rate of the growth-limiting compound, in this case ammonia, we can identify the ammonia uptake rate. From literature values, if we assume that the affinity constant Ks is about 0.03 millimoles of ammonia N per liter, and the maximum uptake rate Qs max is also 0.3 millimoles of ammonia per mole biomass per hour, we can estimate the actual uptake rate of ammonia using the equation from the last slide. Using these values, we find that the uptake rate of ammonia is 0.98 millimoles of ammonia N per mole of biomass produced per hour. In this case, we have defined the growth rate of microorganisms solely based on substrate uptake. But we need to remember that microbes use energy for two main purposes. First, for growth, which involves creating new biomass. And second, for maintenance, which covers basic cellular functions like repair, nutrient transport, and maintaining internal balance. The maintenance can also be written as an equation, which describes the consumption of electron donor and electron acceptor to support cell activity other than growth. In this way, the overall catabolic and anabolic reactions are coupled for one part driving growth and the other supporting maintenance. We can describe this relationship between substrate consumption, growth, and maintenance of cells using the Herbert-Pert concept. It tells us that the substrate uptake rate, QS, can be divided into two parts. One part associated with growth, which depends on the maximum yield of substrate for biomass growth Qx, and describes the flux of electron donor per mole biomass per hour. Another part associated with maintenance, where the yield refers to the catabolic equation. We can rearrange this equation with the maximum yield of substrate per biomass, S per X, also referred to as the inverse of the maximum yield of substrate per biomass, S per X, which can be calculated based on the stoichiometry of the microbial metabolism. The QS becomes mu, the actual biomass-specific growth rate, and maintenance derived from the catabolic equation. The maintenance terms becomes MS, that is the biomass-specific substrate consumption rate for maintenance activities. In this way, the total substrate consumption represents both the energy used by cells for biomass production and the energy required for cellular maintenance. Graphically, we can see two relationships. In the first graph, growth rate mu versus substrate uptake rate Qs, where the intercept corresponds to the maintenance requirement if there is very low growth. You can also appreciate that in the blue dashed lines, depicting maintenance Ms over substrate uptake rate Qs, we see that almost all substrate consumed is directed towards maintenance activities. As the growth rate increases, the experimentally observed substrate uptake rate, that is plotted here, also increases and includes the consumption that is diverted towards maintenance. Therefore, the slope represents the inverse of the maximum yield of biomass per mole substrate consumed. At high growth rate, the blue dashed line depicting maintenance MED over substrate uptake rate Qs shows that the overall substrate consumption, the contribution towards maintenance processes in a cell, decreases. In the second graph, we plot the biomass growth rate, mu, versus the actual observed biomass yield, represented as Yx over S, or yield of biomass per mole substrate consumed. We can see that as the growth rate increases, the yield also increases until it reaches a maximum yield value, beyond which it levels off. This means that at higher growth rates, a smaller fraction of the substrate flux is diverted towards maintenance, and more is directed towards biomass formation. Whereas at low growth rates, most of the substrate consumed goes towards maintenance purposes. Now, let's use this to calculate the actual growth rate for nitrifiers in this example. if the maximum yield of biomass per ammonia is 0.067 moles of biomass per ammonia nitrogen, and the maintenance coefficient is 0.017 moles of ammonia nitrogen per mole of biomass per hour, we can estimate the growth rate. From these values, the growth rate works out to be around 0.018 per hour. This value is important to calculate because it gives us the minimum retention time of biomass, enough for stable operation and efficient treatment of the ammonia-rich wastewater coming into the bioreactor. To summarize, stoichiometry gives us the quantitative relationship between reactants and products, helping us determine how much of the influent is converted into desired products. Kinetics tells us how fast these transformations occur, influencing how we size reactors and operate them efficiently. In this lecture, we derived the stoichiometric relationship of a nitrifier metabolism, calculated the ammonia uptake rate given an influent ammonia concentration, and identified the growth rate per hour for nitrifiers growing in the bioreactor. Together, stoichiometry and kinetics form the foundation of bioprocess design, linking what is converted to how fast it happens and ultimately determining both the performance and cost of environmental biotechnological systems.